Mandelbrot Cascades.
Nice to meet you.
Okay, so thanks a lot for the invitation here, and happy birthday to Leonid. What I'm talking about, this topic, is here are the authors. So there are two students, Mika Nikula and Christian Webb, who have done most of the difficult things, and then there are two colleagues, Saxman and Varel, involved in this thing. So what is the topic? The topic is about random measures on the plane, or in general random measures. This has to do with disordered systems, as you see in a moment, but let me give you some other motivations why these things have been recently sort of looked at. So if you think about, take just the usual area on the plane and multiply it by exponential of the free field. Free field being just the usual quantum field theory without in 2 dimensions. Then and you consider this as a random weight factor. Actually, this factor doesn't really make sense as such. One has to define it as a limit, but we'll come to that later. But anyway, that way of doing, you will have a random measure on the plane, and it has been argued to be interesting from several points of view. For instance, being a model of something related to 2-dimensional gravity, namely telling about putting a random metric actually on the plane, and that having to do with then critical exponents on random surfaces. So this point of view was stressed by Duplantier and Sheffield. If you restrict it onto curves, you end up having a theory of random curves on the plane, sort of complementary to the SLE, actually giving similar curves as SLE, and that was something which we were doing with Astela Jones and Saxman, and also Scott Sheffield was doing it in different geometry. So there is some interest of looking at such things. There's also interest from the point of view of disordered systems, because these random measures seem to have some sort of freezing transition, or sort of baby spin glass type transition. There's the which one is it? This one. There's the one parameter here. Call it beta, like inverse temperature, and when you are in the high temperature, so small beta region, these measures they are continuous. Well, actually singular continuous, but they're continuous. That's an old result by Kahan, and there seems to be a critical point where it's still believed to be continuous, and then above that pure point, so atomic measure. And again, this sort of behavior of these measures are also reflected then in the change of the geometry. So in particular, the high temperature measures, some of the associated random surfaces are believed to be sort of describing conformal field theories of spin systems corresponding to C less than 1 conformal field theories, and on random surfaces, and the associated curves, SLE curves with a kappa parameter less than 4. And then when you go to the low temperature region, then there is the phase transition away from simple curves and away from simple surfaces to this sort of branch polymer surfaces. Okay, so that's that. So much for the background. What I will discuss here is a very simple, although closely related family of measures, which are, from the point of view, if one thinks about them from statistical mechanics or quantum field theory point of view, they are like hierarchical versions of these measures. And these are measures systems which were discussed long time ago by Mandelbrot. So that's why they're called Mandelbrot.
Excuse me, Antti, but I came in a little late. So do you know what happened
temperature case without the hierarchical approximation?
Yes.
That's okay.
This is for the free field.
That's for the free field.
Yeah.
So you know. So those are conjectures or theorems?
This is an old result by Kahan already years ago, or something like 76, I think.
But the other two are conjectural.
Or conjectures are almost proven. Let's put it like that. I think, related things are proven. Not exactly the ones at the moment, but I think it's just a matter of time. And actually, most of the difficulties are already in the cascade case. So let me go through that. So that sort of ties to a disordered system, which is also pretty old and has been discussed a lot, namely the random energy model. And let me start from that. So random energy models are very simple disordered systems where you just think about that your Hamiltonian your Hamiltonian. Say if on a spin system you have n spins. So let's say i's from 1 to n are the sites where the spins are, and they take values. Let me call them 0 and 1, and take the Hamiltonian, a Gaussian random variable with some covariance. Okay, so of course many interesting disordered systems are like that. If I just don't specify at the moment what the covariance is, this is a big class of disordered systems. You consider the random Gibbs measure, so the fix one of these realizations for randomness and consider the Gibbs measure and study that. Now, the simple random energy model, which was introduced by Derrida also a long time ago, is one where the Hamiltonians with different spin configurations are independent. And already that's of course, the Hamiltonians are independent random variables. So studying this measure is pretty much explicit. And indeed, that was understood by Derrida and later by Bouvier, Kurkova, and many other people, that there is phase transition there, namely high temperature phase, where the measure is supported on a continuum of spin configurations. So configurations which grow exponentially with the volume, whereas in the low temperature regime it's supported on a countable set only. And there's also this freezing transition where various quantities like free energy freeze. They don't depend on temperature in the low temperature regime. Now, this is very unrealistic, and there were various random energy models people were building from that. But the simplest and the most interesting one, which corresponds to sort of not too correlated and not too decorrelated, just in the between, is the Mandelbrot Cascade, which is the following. So here you do the following. You don't take independent Hamiltonians, but you build your Hamiltonian by giving a tree. So if I have a finite tree, then the spins are, think about the spins living here, these points, at the branches of the tree. So the tree is of course parameterized by symbols, which tell the list the branches in each generation. And what you do, you put on each line of the tree a random independent identically distributed random variable, a copy of a given one, and then define your energy of the spin configuration here. Give the energy by just summing over all these random variables along the path going down here, and the energy of the next one here. So, for instance, this one, which I could parameterize by number 001, I take this V plus this V plus this V plus that V, and here add those guys. So even if these are are independent, of course the resulting energies of the spins are correlated through the tree structure. So at level n, so when I have n spins, here is the Hamiltonian of each spin configuration is given by the sum of the v's. Okay. So in the beginning I was talking about measures on the plane and on the line. So of course spin configurations can be used to give points on the line. So let me map this to unit interval. So again, if I have a cutoff n here, so I have spin configuration up to with n spins, I can use that to parameterize 2 to the n intervals of length 2 to the minus n on the unit circle. So here is a picture, and then let's just take the measure on the unit interval, where I take the length of that interval and weight it by exponential of minus beta times the Hamiltonian. Okay, so that's a random measure on the unit interval. It's sort of constant on these short intervals. But of course, I'm going to take n to infinity and in the end get some sort of continuum limit of this measure. Okay. So where did this come from? This was sort of an old story. It started with Mandelbrot, who wanted to model intermittency and turbulence, and he noticed that these kinds of measures have that property. Namely, when you look at various moments of the take interval, compute its length, and take moments of that, and take in the randomness, you get sort of multifractal scaling behavior. Each moment has a very its own scaling behavior. And as I said, high temperature phase was understood by Kahan in the 70s, and he also understood the corresponding translation invariant case where you take the free field. The phase transition that this measures has phase transition was already noticed by Kahan and studied by Branson and Duret and Liggett, and later in mathematical physics it was studied by Derrida and Spohn, who were studying especially the low temperature phase. And so it was sort of the study of this thing went on and on for a long period. It was refound the model by Beniamini and Schramm, who wanted to understand these KP-Z relations, who proved them in the context of this model. I will come back to in a moment what these relations. Okay, so that's an interesting class of measures on the unit interval with interesting correlation structure. So, namely, if I, for instance, take 2 of these Hamiltonians, I ask how they are correlated. In the simple REM, they were independent. Here they are correlated sort of logarithmically. It's obvious from the picture here that what is the correlation? Okay, if I take this spin and that spin, then I have to go. All these paths are independent until I go to the common ancestors of the 2 branches. So the correlation between Hamiltonian at one spin and another one, and the covariance goes like the hierarchical distance between the points, so it behaves like logarithm of the distance of the 2 intervals. So in the free field, which is translation invariant, you have exactly logarithmic correlation. Here it's the hierarchical distance. Of course, you can model things on the plane by just taking more symbols. So if you take 4, then I can parameterize squares, dyadic squares on the plane. Also, if I take V Gaussian, then this is nothing but the Dyson hierarchical model of free field with ultraviolet cutoff 2 to the minus n. Okay. Now you want to do the continuum limit. So how to do that. So the n going to infinity limit of this measure when I view it as a measure on unit interval. You have to. The question is how to normalize this measure to get the limit. You would like to ask the question that can you find a normalization constant so that maybe it blows up with the volume, but once you multiply it by that, you get almost surely limit measure, a random measure on the interval. A natural guess is just to normalize it by divided by its expected value. So then you have sort of measures which are whose expected volume of the whole interval is 1 all the time. And indeed, that's natural from the point of view that if you look at the full partition function, so the volume of the whole interval divided by the expected value, then that is a martingale if I view this n as a time. So I add these layers of V, I add these independent guys at each layer, then it's an easy computation to see that this way, normalizing it, you get the martingale. So the expected value is 1 because I divided it by that, and in the case of the Gaussian case, again, this way of normalizing means just that you're weak ordering the exponential. Of course, that's from quantum field theory, that's the first thing that would come to your mind if you have a Gaussian random variable. You weak order it, and then you have something which you in some cases understand that has a continuum limit. Okay, so this works up to a point. Actually, it works in the high temperature region. It's a positive martingale, so it converges almost surely. The question is whether it converges to something non-trivial, and it does it, and that again goes back to Kahan and Perrier. If you are in the high temperature regime, it converges to something positive, so you get actually the partition function. The length of the unit interval is a positive random variable. And however, if you are at the critical temperature or the low temperature region, the limit is 0. Moreover, well, I mean that's the partition function, but then the measures themselves converge, and the limits are continuous measures if you are at the high temperature regime and 0 otherwise. So that's particularly interesting. In the Gaussian case, the critical point is very explicit. It's given by this number here. Now, the same thing holds for the exponential of the free field. So again, you could do the same thing. You put just different scales. You get these martingales, and they converge to something non-trivial in the high temperature and to 0 in the low temperature.
Is beta C the same?
Depends how you normalize your free field, but in suitable units, it's yes. I think the usual normalization is so that it's square root of 2, actually. Okay, so the first question is how to get the non-trivial limit measure if we are in the low temperature regime, and is it continuous or is it pure point? Is it atomic? Now, how to get to this is all long story. Okay, let me go through it nevertheless, sort of slowly. Otherwise, it's not clear what the end one is going to do. So, of course, this hierarchical structure gives you some. There's a lot of structure here, and in particular, if you think about it, if you look at the partition function of the full tree, it's clearly you remember partition function is just you're summing over the spins here, and then with these factors, then obviously partition function with level n is gotten by, well, there's a common factor for each of these guys, which is this. And then there are two identical partition functions which more or less, moreover, are independent because they don't share any v's. So the partition function with cutoff n is simply related to the same partition function at smaller level. So you get a recursion relation for the partition function. So in law you have this, and these are independent. V is independent from those two, and they are independent from each other. So this simple recursion relation, if you plug it into the Laplace transform of this partition function, so that's a random variable. Look at its Laplace transform, and this is what Derrida and Spohn were looking at. They parameterize the Laplace transform with they call the variable t here by e to the minus beta x, which you'll see in a moment why it's convenient. That's because of this prefactor here. So once you plug that into that recursion relation, and using the independence, you get a simple flow equation for the Laplace transform of the partition function as the ultraviolet scale is increased. Okay, so this is just, if you know it for scale n, this equation gives it a scale n plus 1. And here rho is just the density of this V. So for Gaussian, it's just the usual Gaussian. So the continuum limit is gotten just by studying this iteration with the initial condition with a zero, with nothing, the partition function 1. So that's the, when you don't have anything, you have just e to the minus beta x. Okay, so that's, this is of course something very familiar to some people, namely if you go to continuous time, it's a very old observation that you get PD instead of this recursion in time and integral equation. You get parabolic PD when you vary the scale. So t is like my n there. You vary the scale, there will be nonlinear PD, the Kolmogorov Petrovsky-Piskunov equation. And that equation has very interesting properties. It has sort of moving front solutions. So G is exponential of something minus something positive, so it's between 0 and 1. And this equation has solutions which interpolate between the solution 0 and solution 1. A front solution which moves with a certain speed. And what Branson showed is that when you study this, well, unfortunately the time jumped here now. When you study this asymptotics of this as time proceeds, you are moving and you shift your position accordingly. You are going to one of these front solutions, and the way you have to shift is of course the speed of the front. So the m will be asymptotically equal to constant times t. At least the ratio goes to 1. And moreover, the speed is selected by the decay of the initial data, and the decay of the initial data is here. So the beta enters here. That's how the temperature enters.
So this is special to that particular data, or you can use other data?
Oh, very general. Branson's result was very, very general. Okay. So the t going to infinity limit corresponds to continuum limit in our case. Now the thing which was sort of, this was sort of folklore that should be the same for the Cascade too, but it was never really written down. The proof that was done by my student, and more or less, let me summarize the low temperature part, which is the only interesting part for our discussion here. So what happens is, and let me just say to the Gaussian, so when, which is what he proved, when beta is bigger than beta critical or equal, then indeed you have convergence to a function which is independent of beta. Once you shift by the following, so and the shift is there's this square root of 2 log 2 which is hanging around in the Gaussian case all over the place. So there's something linear in n and something logarithmic in n, and the coefficient of the logarithm also changes at critical temperature and not at away. And this coefficient is everything what is this is the important thing as far as the normalization of the measure. So there is a freezing transition, so the limit doesn't depend on beta, and there is this peculiar normalization. So what does this mean? Okay, so let's take this for granted. This is motivated by this PDE, that such a thing happens. What does it imply to our problem? Well, so the theorem is that this guy converges. So if I shift the x by this funny number, then I get the limit. And this was a PDF of the partition function. If you look at what it means, this is you're shifting the x. So it means that I'm looking at my partition function and multiplying by e to the minus beta times this number here. Let's call it little z. And that has a limit as n goes to infinity. So the Laplace transform of that. That, of course, means that these random variables, the partition function normalized this way, has a limit as n goes to infinity. In distribution, of course, because if the Laplace transform converges. So in particular, if you look at what it means, how this m behaves, there is this factor here. When you translate it, what it means that, for instance, at the critical point, in the Gaussian case, weak ordering is not enough. You have to multiply it by square root of n. Once you do that, then you have convergence. It was later, well, actually this year, proven by Eidekon and Shi at the critical point, and Madol in the low temperature phase for very general V's. What I told you was only about the Gaussian. So V is describing the fluctuation field at a given scale, and in this business it can be very general. Okay, so more actually happens. So not only this partition, since I have this hierarchical model, it's enough to control the partition function. You get the whole measure afterwards. And that's also not so difficult to understand if you think about it. If I let's take a dyadic interval on the unit interval, and so how would I normalize the measure? Okay, according to what we wrote here, the weak ordering is more or less here. So that's the leading piece of the speed of the front, and then there was this n to power alpha, which was 2/3 or 3 halves and 1/2, depending on the temperature. Then that way, normalizing the measure, you have a limit. Okay, so these measures converge as n goes to infinity, and actually the limiting measure is given by just this sort of, at the critical point, this weak ordered Hamiltonian times the partition function of the little interval. That's not so difficult to understand, because if you look at the tree, it's obvious that if I keep on going down here, then the true measure of this interval here is just the appropriately scaled partition function of that interval. So that's what it's saying. It's saying that the continuum limit is gotten just by exponential of the Hamiltonian with cutoff times the continuum limit of the partition, copy of the continuum limit of the properly normalized partition function. So knowing the law of these guys gives the law of the limit. Even more is true, namely the low temperature measures are completely determined by the critical measure. That's also sort of a long story, going back to Duret and Liggett, who noticed the following thing. So if you look at what did we get? We got that if I properly normalize, I got this continuum limit of the partition function. Its generating function is given by a function which doesn't depend on temperature. So obviously, when I look at different temperatures here, I vary the beta. The only thing which is varying here is, well, beta is varying here and here. So I can go from one Laplace variable to the other one if I just do a little trick here. So the Laplace transform of any beta variable is related to the critical point, because they are given both by this g here, by this funny funny factor. So if I have t here, I have fractional power of t here. Well, I mean, that of course indicates immediately when you see that, you might come to the conclusion that, well, you can get one from the other by just composing with additional randomness, namely pick a Levy process with the following scaling behavior. So take a Levy process, so the time is s. It has a scaling parameter alpha, so that the generating function is just e to the minus s times t to the alpha. Brownian motion would have t squared here, but here my alpha is here between 0 and 1. So, well, if you compose now, if you look at these two formula, then it's obvious that the low temperature partition function can be gotten from the critical one by composing with this Levy process. Well, but if you can do it for the partition function, the measures were determined by the partition function, so it extends, and that was noted by Barral, Rhodes, and Vargas, that actually the measure of an interval, any interval, is gotten by computed with at the critical point, and then take that as your time of the Levy process. But this Levy process is a pure jump process. So when t proceeds here, this side jumps. So that proves that the low temperature measures are purely atomic. Okay, so all that remains to be understood in the case is the critical point. Everything else is determined. So that's what we did. So first of all, what you can do at the critical point is to show that the critical point measure is still continuous. It's actually zero dimension. So all these measures are singular continuous, but the dimension of the support goes to 0 at the critical point. So it's dimension 0, but it's still continuous. You can also study its modulus continuity. This actually is important if you want to understand then the random curves which are described by this measure by this conformal welding. So maybe it's not so important for the present talk. Then the KPZ relation holds, not only at the high temperature region, but also in the low temperature and critical. Also, the multifractal spectrum is computable. So let me say a few words about that. The continuity is actually from what I told you already, it should be not difficult to believe. I told you that the continuum limit is in distribution the same thing as the exponential of the Hamiltonian times a copy of the partition function. And I also told you that there's this normalization that this guy converges to the partition function as n goes to infinity. I have to put this n to half here. So obviously, once you have some control of the tails, and that's of course hard work, of z, then it's plain that these guys will go to 0 because there's n to half, and the half actually explains exactly the modulus of continuity also of the measure. Okay, since this guy, the max of this has to go like 1 over square root of n. And n is the cutoff of the interval. KPZ relation. So the way it was interpreted by Duplantier and Sheffield is the following. KPZ means Grishnik, Polyakov, and Zamolodchikov, and the relation is old and comes from quantum gravity. But the interpretation by these people was that you think about fractals, say, let's on the unit interval sets. You can compute the Hausdorff dimension in the Euclidean metric, but you can also compute them in a random metric. And the KPZ formula relates those two. We have a random metric because we have a random measure. So that gives, of course, in one dimension rise to a metric by just the obvious thing, namely the length of the interval is the measure of the interval. then there is an explicit relation, namely if I take any set from this unit interval, compute its Hausdorff dimension in the Euclidean metric and in the random metric, then KPZ relation, as it was already done by these people in the more general context, is a formula of that type in the Gaussian case. Explicit relation where those dimensions are related to each other. Of course, in the original formulation, these were sort of phase boundaries in say Ising model and an Ising model on a random surface. But here we are talking just about relations of dimensions of fractals in these two measures. This was proven by Beniamini and Schramm in the low temperature phase. At the critical point, the measure still continues, and actually one can do a proof there, and then for the low temperature phase, since that was just gotten by scale invariant process acting on the critical point, the relation there is very simple. So everything is determined once you understand the critical relation again. The proof goes in the usual way that first of all you need to sort of get an upper bound and a lower bound. Upper bound is for the upper bound you need to control 1 point functions of these measures, and this is an old calculation. This is what Mandelbrot already knew, namely this is the multifractal exponent multiscaling of the measure. So that explains where this relation comes from, and then to prove that it's actually the truth, you need a lower bound for which you need to control the 2-point function. And in this case, I think it's hierarchical. That's not a very difficult thing. One can also study extreme value statistics here. Maybe when did I start?
I have 3 minutes.
3 minutes. Okay. If you go to infinite temperature, then you have then you're looking at just how is the maximum. Zero temperature. Infinite beta, 0 temperature. Then how is the maximum of these random variables distributed? And of course, if you have independent random variables, you know that once you take the maximum and properly shift it, you get the Gumbel distribution. So having this exponential of minus exponential kind of tail behavior. And in the cascade, well, the shift is very concrete. That's just the shift which I already showed you once. And the fact that we converge immediately gives you, converge to this function g here, immediately gives you then that the distribution answer to this question, how is the maximum distributed, is given by this little g, and that little g can be computed. Its asymptotics can be computed. So, and it's not in the Gumbel class. So there is this extra x here. As far as the free field, it's of course different. If I think about Mandelbrot Cascade, it's just a hierarchical field, which one way to describe that is that on the lattice, just take dyadic squares, say on the 1 dimension or 2 dimension. I take here 2 dimension. Dyadic squares, and put at each dyadic square an independent identical distributed random variable. That's what we did. And take the field as sum from n to your ultraviolet cutoff of these guys. Namely, at field at point x just collects all the dyadic squares at different scales to which x belongs. At each scale there's only 1 square, and you sum over them. So all these fluctuation fields are independent at different points. In free fields, they are weakly dependent. So they are not independent. you can do it so that sort of close by guys are independent, but not exactly. And that, of course, makes, as you know, many things much more tedious. So, in fact, this randomization group map, which we had, was very local here, becomes non-local. And that's one of the things which becomes more complicated. What is known about it? It's well understood, as I told you, below the in high temperatures, at infinite temperature, a lot is already understood by both House and Zaituni and Branson and other people. So the maximum, the expected value is explicit, and it's shown that once you subtract that, you have tightness. There's even an explicit distribution in a particular realization of the free field by Fedorov and Bouchot. That means that I'm okay. And many other things. So there is statistics of the nearby points. There's a portion of digital statistics proven by these people and so on. But none of this actually so far has been able to go all the way to prove that the convergence of the measure know that if the limit exists and whether it's atomic. Why is this interesting? I mean, this is just the starting point of this random geometry business. Namely, once you have these measures, we like to understand what sort of geometry they give rise to. Do they, in 2 dimensions, for instance, give rise to a random metric space? The random measure is not the same thing as a metric in 2 dimensions. What is the Hausdorff dimension, etc.? Simpler question, what I've been involved in is take the 1-dimensional case, take the free field restricted on the circle, for instance. You can there's a device with which such gluing disks with such random measures gives you random curves on the plane, and they are curves which have very similar properties to SLE. So that's sort of an alternative construction of random curves on the plane. And this point of view was, of course, stressed a lot by Scott Sheffield also. Again, here it's very open what to do in the low temperature regimes. We understand a little bit what to do in the high, in this particular case, a lot what to do in the high temperature regime, but what happens at the critical point and in the low temperature regime is wide open. And here it's even in the high temperature regime quite open what to do. Okay, thank you.
Thank you very much for the questions, comments. So that seems not to be the case. Let's thank the speaker again.